Hello, everybody. Welcome to a very special and the first edition of Reading with Levi. I am your host, Levi, and today's book that we will be taking a look at is How to Lie with Maps. This is a book that was written by Monmonier. We're going to be reading the third edition, and I hope it's not a problem. I'm not going to be reading the preface. I am just reading this book for my World Geography class. And I figured that the best way to read a book, in my opinion, is out loud, and that way I can also watch this back later and take better notes, because I am terrible when it comes to writing down notes for books. So everybody, if you have this book, grab it, get ready, get some popcorn. Maybe don't, that'd probably not be good for your pages, but settle down and let's get cozy and let's read, shall we? Chapter 1. Introduction. Not only is it easy to lie with maps, it's essential. To portray meaningful relationships for a complex, three-dimensional world on a flat sheet of paper or a screen, a map must distort reality. As a scale model, the map must use symbols that almost always are proportionally much bigger or thicker than the features they represent. To avoid hiding critical information in a fog of detail, the map must offer a selective, incomplete view of reality. There's no escape from the cartographic paradox. To present a useful and truthful picture, an accurate map must tell white lies. Because most map users willingly tolerate white lies on maps, it's not difficult for maps to also tell more serious lies. Map users have traditionally been a trusting lot. They understand the need to distort geometry and suppress features, and they believe the cartographer really does know where to draw the line, figuratively as well as literally. As with many things beyond their full understanding, they generally entrust mapmaking to a priesthood of technically competent designers and geographers working for government agencies and commercial firms. Yet, cartographers are not licensed, and many map makers competent in commercial art or in the use of graphic software have never studied cartography. Even map users who know that such software is widely available and who see maps in an increasing range of media seldom question these authorities, as they often fail to appreciate the map's power as a tool of deliberate falsification or subtle propaganda. Because anyone with the right software and an internet connection can now make and publish maps, map makers can also easily lie to themselves and others and be unaware of it. Before the electronic age, folk cartography consisted largely of hand-drawn maps giving directions. The direction giver had full control over pencil and paper and usually had no difficulty transferring routes, landmarks, and other relevant recollections from mind to map. But the result was clearly amateurish. Technology allows people without cartographic savvy to create modern-day folk maps with the crisp type, uniform symbols, and verisimilitude of maps from the cartographic priesthood. Yet, software developers have also made it easy for the lay cartographer to select inappropriate projection or a misleading set of symbols. Because of advances in graphic software and online mapping, inadvertent yet serious cartographic lies can appear respectable and accurate. The potential for cartographic mischief extends well beyond the deliberate manipulation used by some cartographer propagandists and the electronic blunders made by the cartographically ignorant. If any single caveat can alert map users to their unhealthy but widespread naivety, it is that a single map is but one of an indefinitely large number of maps that might be produced for the same situation or from the same data. The italics reflect an academic lifetime of browbeating undergraduates with this obviously but readily ignored warning. How easy it is to forget, and how revealing to recall, that map authors can experiment freely with features, measurements, area of coverage, and symbols, and can pick the map that best presents their case or supports their unconscious bias. Map users must be aware that the cartographic license is enormously broad. The purpose of this book is to promote a healthy skepticism about maps, not to foster either cynicism or deliberate dishonesty. In showing how to lie with maps, I want to make readers aware that maps, like speeches and paintings, are authored collections of information and are also subject to distortions arising from ignorance, greed, ideological blindness, or malice. Examining the misuses of maps, both paper and digital, also provides an interesting introduction to the nature of maps and their range of appropriate uses. The 4 chapters that follow this one address general cartographic principles that apply to all different types of maps. Chapter 2 considers the map's main elements, scale, projection, and symbolization, as potential sources of distortion, while Chapter 3 further explores the effects of scale by examining the various white lies cartographers justify as necessary generalization. And Chapter 4 looks at common blunders resulting from the mapmaker's ignorance or oversight. Chapter 5 looks at how a careless or Machiavellian choice of colors can confuse or mislead the map viewer. The rest of the chapters treat specific types of maps and how they can be manipulated. Chapter 6 treats the seductive use of symbols in advertising maps, and Chapter 7 explores the exaggeration and suppression in maps prepared for the development plans and environmental impact statements. Chapter 8 and 9 examines distorted maps by using governments as political propaganda and as disinformation for military opponents. Government mapping is also a central concern in Chapter 10, which investigates the effects of national culture and bureaucratic inertia, and increasingly commercial interest on detailed topographic maps. Chapter 11 addresses distortion and self-deception in maps made from census and survey data and other quantitative information. Chapter 12 examines the specific challenges posed by image maps that are based on satellite technology and other measurements. Chapter 13 acknowledges the emergence of prohibitive mapping as a pervasive and potentially threatening cartographic genre, and Chapter 14 addresses the diverse types of dynamic maps and the distinctive advantages and constraints of online maps. Chapter 15 concludes by noting how maps can have dual and sometimes conflicting roles, and by recommending a skeptical assessment of a map author's motives. I apologize if there's any is or just general misspoken words. I apologize. In an era of increasing skepticism about the nature of knowledge, a book about what it means to lie with maps is more useful than ever. For all the interest in verbal lies, nefarious as well as white, and in how words can be manipulated, education in the use of maps and other visuals is spotty and limited, and many otherwise educated people are graphically and cartographically illiterate. Maps, like numbers, are often arcane images accorded undue respect and credibility. This book's principal goal is to dispel this cartographic mystique and promote a more informed use of maps based on an understanding and appreciation of their flexibility as a medium of communication. As technology continues to lower the barriers dividing map users from map makers, this book's insights can be especially useful for those who might more effectively use maps in their work or as citizens fighting environmental deterioration or social ills. The informed skeptic becomes a perceptive map author, better able to describe locational characters and explain geographic relationships, and better equipped to recognize and counter the self-serving arguments of biased or dishonest mapmakers. Chapter 2. Elements of the map. Maps have 3 basic attributes: scale, projection, and symbolization. Each element is a source of distortion. As a group, they describe the essence of the map's possibilities and limitations. No one can use maps or make maps safely and effectively without understanding map scales, map projections, and map symbols. Scale. Most maps are smaller than the reality they represent, and map scales tell us how much smaller. A map can state its scale in 3 ways: as a ratio, as a short sentence, or as a simple graph. Figure 2.1 shows some typical statements of map scale. Ratio scales relate 1 unit of distance on the map to a specific distance on the ground. The units must be the same, so that a ratio of 1 to 10,000 means that a 1-inch line on the map represents a 10,000-inch stretch of road, or that 1 centimeter represents 10,000 centimeters, or 1 foot stands for 10,000 feet. As long as they are the same, the units don't matter and need not be stated. The ratio scale is a dimensionless number. By convention, the part of the ratio to the left of the colon is always 1. Some maps state the ratio scale as a fraction, but both forms have the same meaning. Whether the mapmaker uses 1 to 24,000 or 1 over 24,000 is solely a matter of style. Fractional statements help the user compare map scales. A scale of 1 over 10,000 or 1 10,000 is larger than a scale of 1 over 250,000 or 1 250,000 because 1 over 10,000 is a larger fraction than 1 over 250,000. Here's a picture for any who wants to look at it. Recall that small fractions have big denominators and big fractions have small denominators, or that a half of a pie is more than a quarter of the pie. In general, large-scale maps have scales of 1 24,000 or larger, whereas small-scale maps have scales of 1 500,000 or smaller. But these distinctions are relative. In a city planning office where the smallest map scale is 1 50,000, small scale might refer to the maps at 1 24,000 or smaller, and large scale to maps at 1 4,800 or larger. Large-scale maps tend to be more detailed than small-scale maps. Consider two maps, one at 1 10,000 and the other at 1 10 million. A 1-inch line at 1 10,000 represents 10,000 inches, which is 833 1/3 feet, or roughly 0.16 miles. At this scale, a square measuring 1 inch on each side represents an area of 0.025 square miles, or roughly 16 acres. In contrast, at 1 10 million, the 1-inch line on the map represents almost 158 miles, and the square inch would represent an area slightly over 24,900 square miles, or nearly 16 million acres. In this example, the square inch on the large-scale map could show features on the ground in far greater detail than the square inch on the small-scale map. Both maps would have to suppress some details, but the designer of the 1 10 million scale map must be far more selective than the cartographer producing the 1 10,000 scale map. In the sense that all maps tell white lies about the planet, small-scale maps have a smaller capacity for truth than large-scale maps. Verbal statements, such as 1 inch represents 1 mile, relate units convenient for measuring distances on the map to units commonly used for estimating and thinking about distances on the ground. For most users, this simple sentence is more meaningful than the corresponding ratio scale of 1 63,360, or its close approximation, 1 62,500. British map users used to identify various map series with adjective phrases such as inch to the mile or 4 miles to the inch, a close approximation for 1 250,000. Sometimes a map maker might say equals instead of represents. Although technically absurd, equals in these cases might more kindly be considered a shorthand for is the equivalent of. Yet the skeptic rightly warns of cartographic seduction, for 1 inch equals 1 mile. Not only robs the user of a subtle reminder that the map is merely a symbolic model, but also falsely suggests that the mapped image is a reality. As later chapters show, this delusion can be dangerous. Metric units make verbal scales less necessary. Persons familiar with centimeters and kilometers have little need for sentences to tell them that at 100,000, 1 centimeter represents 1 kilometer, or that at 125,000, 4 centimeters represents 1 kilometer. In Europe, where metric units are standard, round number map scales of 1 10,000, 1 25,000, 1 50,000, and 1 100,000 are common. In the United States, where the metric system's most prominent inroads have been in the liquor and drug businesses, large-scale maps typically represent reality at scales of 1 9,600. 1 inch represents 800 feet. 1 24,000, 1 inch represents 2,000 feet, and 1 62,500. 1 inch represents slightly less than 1 mile. Graphic scales are not only the most helpful means of communicating map scale, but also the safest. An alternative to blind trust in the user's sense of distance and skill in mental arithmetic, the simple bar scale typically portrays the series of conveniently rounded distances appropriate to the map's function and the area covered. Graphic scales are particularly safe for maps that might be reduced or enlarged for publication or by users. For example, a 5-inch wide map labeled 1/50,000 would have a scale less than 1/80,000 if reduced to fit a newspaper column or a mobile device screen that is 3 inches wide, whereas a scale bar representing a half mile would shrink along with the map's other symbols and distances. Ratio and verbal scales are useless on digital maps since screens and thus the map scales vary widely and unpredictably. Web-based maps and similar interactive applications occasion a fourth type of map scale, the zoom slider that moves up and down to indicate relative distance above the surface, or the interactive plus and minus buttons that produce the same effect. Zooming out yields a broader geographic scope with a smaller scale and less detail, and zooming in provides a narrower view with a greater detail. Map projections. Map projections, which transform the curved three-dimensional surface of the planet into a flat two-dimensional plane, can greatly distort map scale. Although the globe can be a true scale model of the Earth, without a constant scale at all points and in all directions, the flat map stretches with distances and shortens others, so that the scale varies from point to point. Indeed, the bar scale sometimes included in the lower right of an online map can be blatantly misleading when the user zooms out to show an entire continent. Moreover, scale at a point tends to vary with direction as well. The world map projection in Figure 2.2 illustrates the often severe scale differences found on maps portraying large areas. In this instance, map scale is constant along the equator and the meridians, which are shown as straight lines perpendicular to the equator and running from the North Pole to the South Pole. Here's the thingy. The terms parallel, meridian, latitude, and longitude seem puzzling. The quick review of basic world geographic concepts found in the appendix might be helpful, because if the meridians have the same scale as the equator, each meridian, if we assume the Earth is a perfect sphere, is half the length of the equator. Because scale is constant along the meridians, the map preserves the even spacing of parallels spaced by 30 degrees of latitude. But on this map, all parallels are the same length, even though on the Earth or a globe, parallels decrease in length from the equator to the poles. Moreover, the map projection has stretched the poles from points with no length to lines as long as the equator. North-south scale is constant, but the east-west scale increases to twice the north-south scale at 60 degrees north and 60 degrees south, and to infinity at the poles. Ratio scales commonly describe a world map's capacity for detail, but the scale is strictly valid for just a few lines on the map. In the case of Figure 2.2, it is valid only for the equator and the meridians. Most world maps don't warn that using the scale ratio to convert distances between map symbols to distances between real places almost always yields an erroneous result. Figure 2.2, for instance, would greatly inflate the distance between Chicago and Stockholm, which are far apart and both well north of the equator. Cartographers wisely advise decorating world maps with graphic scales, which might encourage this type of abuse. In contrast, scale distortions of distance usually is negligible on large-scale maps where the area covered is comparatively small. Figure 2.3 helps explain the meaning and limitations of ratio scales in world maps by treating map projections as a two-stage process. Stage 1 shrinks the Earth to a globe for which the ratio scale is valid everywhere and in all directions. Stage 2 projects symbols from the globe onto a flattenable surface such as a plane, a cone, or a cylinder, which is attached to the globe at a point or at one or two standard lines. On flat maps, the scale usually is constant only along these standard lines. In Figure 2.2, a type of cylindrical projection called a plane chart, The equator is a standard line, and the meridians show true scale as well. In general, scale distortion increases with distance from the standard line. The common developable surfaces, plane, cone, and cylinder, allow the mapmaker to minimize distortion by centering the projection in or near the region featured on the map. World maps commonly use a cylindrical projection centered on the equator. Figure 2.4 shows that a secant cylindrical projection, which cuts through the globe, yields two standard lines, whereas a tangent cylindrical projection, which merely touches the globe, has only one. Average distortion is less for a secant projection because the average place is closer to one of the two standard lines. Conic projections are well suited to large mid-latitude areas such as North America, Europe, and Russia, and secant conic projections offer less average distortion than the tangent conic projections. Azimuthal projections, which use the plane as their developable surface, are used most commonly for maps of polar regions. For each developable surface, he really loves this word, the mapmaker can choose from a variety of projections, each with a unique pattern of distortion. Some projections, called equivalent or equal area, allow the mapmaker to preserve areal relationships. I apologize if that was wrong. Thus, if South America is 8 times larger than Greenland on the globe, it will also be 8 times larger on an equal area projection. Figure 2.5 shows 2 ways to reduce the areal distortion of the plane chart in figure 2.2. The cylindrical equal area projection at the top compensates for severe poleward exaggeration by reducing the separation of the parallels as distance from the equator increases. In contrast, the sinusoidal projection below maintains true scale along the equator, all other parallels, and the central meridian at the same time pulls the meridian inwards towards the poles, compensating for the areal exaggeration that would otherwise occur. And then here's a picture. Distortion is least pronounced in a cross-shaped zone along the equator, and the central meridian and most severe between these axes towards the edge of projection. Despite the highly distorted shapes in these corners, the areas of continents, countries, and belts between adjoining parallels are in correct proportion. Reduced distortion around the central meridian suggests that a sinusoidal projection centered on a meridian through, say, Kansas, might yield a decent equal area representation of North America, whereas a sinusoidal projection with a straight line central meridian passing between Warsaw and Moscow would afford a suitable companion view of the Eurasian landmass. In the early 1920s, the University of Chicago geography professor J. Paul Good extended this notion of a zoned world map and devised the composite projection in figure 2.6. Good's interrupted homolocine equal area projection has 6 lobes, which join along the equator. To avoid severe pinching of the meridians towards the poles, Good divided each lobe into 2 zones at about 40 degrees, an equatorial zone based on the sinusoidal projection and a poleward zone in which the equal area mole-wide projection portrays high latitude areas with less east-west compression. Good's projection mollifies the trade-off of more distorted shapes for the true relative areas by giving up the continuous oceans for less severely distorted landmasses. If interrupted over the land to minimize distortion of the oceans, Good's projections can be equally adept at serving studies of fisheries and other marine elements. No flat map can match the globe in preserving areas, angles, gross shapes, distances, and directions, as any map projection is a comprised solution, yet Good's projection is a particularly worthy compromise when the mapmaker uses dot symbols to portray the worldwide density pattern of population, hogs, wheat, or other dry land variables. On the dot distribution map, with one dot representing 500,000 swine, for example, the spacing of these dots represent relative density. Important hog-producing regions, such as the American Midwest and southeastern China, have many closely spaced dots, whereas hog-poor regions, such as India and Australia, have few. but a projection that distorts area might show contrasting densities for two regions of equal size on the globe and with similar levels of hog production. If both regions have 40 dots representing 20 million swine, the region occupying 2 square centimeters of the map would have a greater spacing between dots and appear less intensively involved in raising pigs than the region occupying only 1 square centimeter. Okay, quick pause break. I'm supposed to write notes and stuff on this book. Where do I start? Do I talk about the pigs? Okay. Sorry. Now I lost my train of thought. Oh no. Projections that are not equal area encourage such spurious inferences. Equivalence is also important when the map user might compare the sizes of countries or the areas covered by various map categories. As equal area projections preserve areas, conformal projections preserve local angles. That is, on a conformal projection, the angle between any two intersecting lines will be the same on both a globe and a flat map. By compressing three-dimensional physical features onto a two-dimensional surface, a conformal projection can noticeably distort the shapes of long features. But within a small neighborhood of the point of intersection, scale will be the same in all directions and shape will be correct. Another picture for y'all. Thus, tiny circles on the globe remain tiny circles on a conformal map. As with all projections, though scale still varies from place to place, and tiny circles identical in size on the globe can vary markedly in size on a conformal projection covering a large region. Although all projections distort the shapes of continents and other large territories, in general, a conformal projection offers a less distorted picture of a gross shape than a projection that is not conformal. Perhaps the most striking trade-off in map projection is the between conformality and areal equivalence. Although some projections distort both angles and areas, no projection can be both conformal and equivalent. Not only are these properties mutually exclusive, but in parts of the map well removed from the standard lines, conformal maps severely exaggerate area and equal mass maps severely distort shapes. Two conformal projections useful in navigation illustrate how badly a map can distort area. The Mercator projection, I love the Mercator, on the left side of figure 2.7 renders Greenland as large as South America, whereas a globe would show Greenland as only about 1/8 as large. Another picture. North-south scale increases so sharply towards the poles that the poles themselves lie at infinity and never appear on an equatorially centered Mercator map. I'm sorry, I'm butchering all these words. The right side of figure 2.7 reveals an even more severe distortion of area on the mnemonic projection, which cannot portray even half the globe. Why then are these projections used at all? Although presenting two of the worst possible perspectives for general purpose base maps and wall maps, these maps are of enormous value to the navigator with a straight edge. On the Mercator map, for instance, a straight line is a rhumb line or loxodrome, which shows an easily followed route of constant bearing. A navigator at A can draw a straight line to B, measure with the protractor the angle between the rhumb line and the meridian, and use this bearing and a corrected compass to sail or fly from A to B. On the mnemonic map, in contrast, a straight line represents a great circle and shows the shortest course from A to B. An effective navigator would have identified a few intermediate points on the great circle route, transfer these course adjustment points from the mnemonic map to the Mercator, mark a chain of rhumb lines between successive intermediate points, measure each rhumb line bearing, and proceed from A to B along a compromise course of easily followed segments that collectively approximate a shortest distance route. Map projections distort 5 geographic relationships: area, angles, gross shapes, distance, and directions. Although some projections preserve local angles but not areas. Others preserve areas but not local angles. All distort large shapes noticeably, but some distort continental shapes more than others, and all distort at least some distances in some directions. Yet, as the Mercator and mnemonic maps demonstrate, the mapmaker often can tailor the projection to serve a specific need. For instance, the oblique azimuthal equidistant projection in figure 2.8 shows true distance and directional relationships for the shortest distance great circle routes converging on Chicago, Illinois. Although highly useful for someone concerned with the relative proximity to Chicago, this projection is of no use for the distance comparisons not involving Chicago. Moreover, its poor portrayal of the shapes and relative areas of continents, especially when extended to a full world map, limits its value as a general purpose reference map. Without an interactive graphic system and good mapping software, of course, map users can be their own highly versatile map makers and tailor projections to many unique needs. For instance, an azimuthal equidistant map centered on North Korea might better inform a discussion of a possible missile attack by a rogue nation than concentric circles drawn thoughtlessly on an off-the-shelf world map. Where does this come into play? Among the more highly tailored map projections are cartograms, which portray relative measures as travel time, transport costs, and population size. Although a more conventional map might address these with tailored symbols and a standard projection, the geometry and layout of the cartogram makes a strong visual statement of distance or area relationships. Here's a picture again. The distance cartograms in Figure 2.9, for example, provide a dramatic comparison of two postal rates, which define different transport cost spaces for their focal point. Syracuse, New York. Note that the rate for a 2-pound parcel mailed to Watertown, New York, is a little more than half the rate from Syracuse to Phoenix, Arizona, whereas the corresponding rates for a 10-pound parcel more nearly reflect Watertown's relative proximity, only 70 miles north of Syracuse. Oh, I'm so sorry about that. Also, my grandpa was born in Phoenix, so big ups, Papa. I love you. These schematic maps omit boundaries and other traditional frame of reference features which are less relevant here than the names of the destinations shown. Coastlines and some national boundaries are more useful in Figure 2.10, an area cartogram, which even includes the pseudogrid to create the visual impression of the world on a torus. The projection is a demographic base map on which the relative sizes of aerial units represent population, not land area. Note that the map portrays India as vastly larger than Canada because the Indian population is more than 35 times larger than Canada's population, even though Canada's area of 3.8 square miles is markedly larger than India's 1.2 million square miles. The cartogram has merged some countries with smaller populations. There's another one. Demonstrating the mapmaker's political insensitivity in sacrificing nationalism for clarity, yet traditionalist cartographers who scorn cartograms as foolish, inaccurate cartoons ignore the power of map distortions to address a wide array of communicational and analytical needs. Excuse me. Map symbols. Graphic symbols complement map scale and projection by making visible the features, places, and other locational information represented on the map. By describing and differentiating features and places, map symbols serve as a graphic code for storing and retrieving data in a two-dimensional geographic framework. This code can be simple and straightforward, as on a route map drawn to show a new neighbor how to find the local elementary school. A few simple lines, labels, and X's representing selected streets and landmarks should do. Labels such as Elm Street and Fire Department tie the map to reality and make a key or legend unnecessary. When the purpose of the map is specific and straightforward, selection of map features also serve to suppress unimportant information, but maps mass-produced by the government, mapping agencies, and commercial map publishers must address a wide variety of questions, and the map symbols must tell the user what's relevant and what isn't. Without the map maker present to explain unfamiliar details, these maps need symbolic code based on an understanding of graphic logic and the limitations of visual perception. A haphazard choice of symbols, adequate for the labels and little pictures of wayfinding maps and other folk cartography, can fail miserably on general purpose maps rich in information. Some complex, such as geologic maps and weather charts, have complex but standardized symbologies that organize an enormous amount of data meaningful only to those who understand the field and its cartographic conventions. Although as arcane to most people as a foreign language or higher mathematics, these maps also benefit from symbols designed according to principles of logic and communication. Appreciating the logic of map symbols begins with understanding the 3 geometric categories of map symbols and the 6 visual variables shown in Figure 2.11. Symbols on a flat map are either point symbols, line symbols, or area symbols. Road maps and most other general-purpose maps use combinations of all 3. Point symbols to mark the locations of landmarks and villages, line symbols to show the lengths and shapes of rivers and roads, and area symbols to depict the form and size of state parks and major cities. By contrast, statistical maps which portray numerical data commonly rely on a single type of symbol, such as dots that denote 10,000 people or gray tones representing election results by county. Maps need contrasting symbols to portray geographic differences. As Figure 2.11 illustrates, map symbols can differ in size, shape, gray tone value, texture, orientation, and hue. That is, color differences. As between blue, green, and red, see Chapter 5, each of these 6 visual variables excels in portraying one kind of geographic difference. I hope that was still recording. My computer just shut off. Uh-oh. Anyways, here's that. Shape, texture, and hue are effective in showing qualitative differences. Why? As between types of land use or dominant religions. For quantitative differences, size is more suited to showing variation in amount or count, such as the number of television viewers by market area, whereas gray tone value is preferred for portraying differences in rate or intensity. Also, I'm going to show the picture again because I realized I didn't get the full scale when I did my last recording. I'm sorry. Please don't be mad at me. Such as the proportion of viewing audience watching the 7th game of the World Series. Blue Jays should have won. Symbols varying in orientation are useful mostly for representing winds, migration streams, troop movements, and other directional occurrences. Another picture. What is happening out there? Some visual variables are unsuitable for small point symbols and thin line symbols that provide insufficient contrast with a background. Hue, for instance, is more effective at showing differences in kind of area symbols than for tiny point symbols, such as dots on a dot distribution map. Gray tone value, which usually works well in portraying percentages and rates for area symbols, is visually less effective with point and line symbols, which tend to be thinner than area symbols. Point symbols commonly rely on shape to show differences in kind and on size to show differences in amount. Line symbols usually use hue or texture to distinguish rivers from railways and town boundaries from dirt roads. Size is useful in representing magnitude for links in a network. A thick line readily suggests greater capacity or heavier traffic than a thin line implies. Area symbols usually are large enough to reveal differences in hue, gray tone, and pattern, but a detail in set with a larger scale might be needed to show a very small yet important aerial units. Some symbols combine 2 visual variables, for example, the elevation contours on a topographic map involving both orientation and spacing. An element of pattern as Figure 2.12 demonstrates, a contour's line direction indicates the local direction of slope because the land slopes downward perpendicular to the trend of the contour line. I really hope if you guys are reading this, you're not asleep, because no offense to Mr. Monmonier, but I'm tired, man. And the spacing of the contour lines shows the relative tilt of the land because close contours mark steep slopes and separated contours indicate gentle slopes. Similarly, the spread of dots on a dot distribution map may show the relative size of hog-producing regions, whereas the spacing or clustering of these dots reveals the relative intensity and geographic concentration of production. A poor match between the data and visual variable can frustrate or confuse the map user. Among the worst offenders are novice mapmakers seduced by the brilliant colors of electronic displays and color printers into using reds, blues, greens, yellows, and oranges to portray quantitative differences. Contrasting hues, however visually dramatic, are not appropriate substitute for a logical series of easily ordered gray tones, except among physicists and professional colorists who understand the relation between hue and wavelength of light maps. Between hue and wavelength of light, map users cannot easily and consistently organize colors into an ordered sequence, and those with imperfect color vision might not even distinguish reds from greens. Yet most map users can readily sort 5 or 6 gray tones evenly spaced between light gray and black, decoding a symbol which, when darker means more and lighter means less. A legend might make a bad map useful, but it can't make it efficient. My throat is starting to hurt from talking so much. Area symbols are not the only ones useful for portraying numerical data for states, counties, and other aerial units. If the map must emphasize magnitudes such as the number of inhabitants rather than intensities such as the number of persons per square mile, point symbols varying in size are more appropriate than area symbols varying in gray tone. The two aerial unit maps in Figure 2.13 illustrates the different graphic strategies required for portraying population size and population density. The map on the left uses graduated point symbols positioned near the center of each area, and the size of the point symbol represents population size. At its right, a choropleth map uses a gray tone symbol that fills the aerial units. The relative darkness of the symbols shows the concentration of population on the land. You know, I kind of want to talk about right now. Sorry, guys. Here's the first image there. Because the visual variables match the measures portrayed, the maps are straightforward and revealing. At the left, big point symbols represent large populations, which occur in both large and small areas, and small point symbols represent small populations. On the choropleth mapped on the right, a dark symbol indicates many people occupying a relatively small area, whereas a light symbol represents either relatively few people in a small area or many people spread rather thinly across a large area. Figure 2.14 illustrates the danger of an inappropriate match between measurement and symbol. Both maps portray population size, but the choropleth map at the right is misleading because its area symbols suggest intensity, not magnitude. Note, for instance, that the dark gray tone representing a large county with a large but relatively sparsely distributed population also represents a small county with an equally large but more densely concentrated population. In contrast, the map at the left provides only a more direct symbolic representation of population size, but a clear picture of area boundaries and area size. The map user should be aware of spurious choropleth maps based on magnitude, yet suggesting density or concentration. Form and color make some map symbols easy to decode. Pictorial point symbols effectively exploit familiar forms, as when little tents represent campgrounds and tiny buildings with crosses on the top indicate churches. Here's the second image. Alphabetic symbols also use form to promote decoding, as with the common abbreviations PO for post office, place names like Baltimore, and labels describes the type of features, Union Pacific Railroad. Color conventions allow map symbols to exploit idealized associations of lakes and streams with a brightly non-murky blue and wooded areas with a wholesome spring-like green. Weather maps take advantage of perceptions of red as warm and blue as cold. Similarly, dashed lines might connote uncertainty in the location of geologic fault line, while mildly transparent areas symbols avoid graphic conflict with useful line symbols otherwise omitted. Color codes often rely more on convention than on perception, as with land use maps, where red commonly represents retail sales and blue stands for manufacturing. Physical political references maps found in atlases and on schoolroom walls reinforce the convention of hyposymmetric tints. A series of color-coded elevation symbols ranging from greens to yellows to browns, although highly used for those who know the code. Elevation tints invite misinterpretation among the unwary, and the greens used to represent lowlands, for instance, might suggest lush vegetation, whereas the browns representing highlands can connote barren land. Despite the many lowland deserts and highland forests throughout the world, like map projections, map symbols can lead naive users to the wrong conclusions. I'm going to take a little break. We are so back. All right. Chapter 3, Map Generalization. Little white lies, and lots of them. A good map tells a multitude of little white lies. It suppresses the truth to help help the user see what it needs to help the user see what needs to be seen. Reality is three-dimensional, rich in detail, and far too factual to allow a complete yet uncluttered two-dimensional graphic scale model. Indeed, a map that did not generalize would be useless, but the value of the map depends on how well its generalized geometry and generalized content reflect a chosen aspect of reality. Geometry. Clarity demands geometric generalization because map symbols usually occupy proportionately more space on the map than the features they represent occupy on the ground. For instance, a line 1/50 inch wide representing a road on a 1/100,000 scale map is the graphic equivalent of a corridor 167 feet wide if a road's actual right-of-way was only 40 feet wide. Say a 1/50 inch wide line symbol would claim access territory at scales smaller than 1/24,000. At 1/100,000, the road symbol would crowd out sidewalks, houses, lesser roads, and other features. And at still smaller scales, more important features might eliminate the road itself. The more important features could include national, state, or country boundaries, which have no width whatsoever on the ground. Point, line, and area symbols require different kinds of generalization. For instance, cartographers recognize the five fundamental processes of geometric line generalization described in Figure 3.1. First, of course, is the selection of complete features for the map. Selection is a positive term that implies the suppression or non-selection of most features. Ideally, the map author approaches selection with the goals to be satisfied by a well-chosen subset of all possible features that might be mapped, and by map symbols chosen to distinguish unlike features and provide a sense of graphic hierarchy. Picture. Features selected to support the specific theme for the map usually require more prominent symbols than background features. Chosen to provide a geographic frame of reference, selecting background details that are effective in relating new information on the map to the viewer's geographic savvy and existing mental map often requires more insight and attention than selecting the map's main features. In the holistic process of planning a map, feature selection is the prime link between generalization and overall design. The four remaining generalization processes in Figure 3.1 alter the appearance and spatial position of linear map features that are represented by a series of points stored electronically as a list of two-dimensional XY coordinates. Although the growing use of software to generalize maps has led to the isolation of these four generalization operations, traditional cartographers perform essentially the same operations manually. At a graphics workstation or with a pen and ink, but typically do so with less structure, less formal awareness, and less consistency than a computer algorithm. Simplification, which reduces detail and angularity by eliminating points from the list, is particularly useful if excessive detail was captured in developing a cartographic data file, or if a data developed for display at one scale are to be displayed at a smaller scale. Displacement avoids graphic interference by shifting apart features that otherwise would overlap or coalesce. A substantial reduction in scale, say from 1 to 25,000 or 1 to 1 million, usually results in the incomprehensible congested collection of map symbols that call for eliminating some features and displacing others. Smoothing, which also diminishes details and angularity, might displace some points and add others to the list. A prime objective of smoothing is to avoid a series of abruptly joined straight line segments. Enhancement adds detail to give map symbols a more realistic appearance. Lines representing streams, for instance, might be given a typical meander loops, whereas shorelines might be made to look more coast-like. Enhanced map symbols are more readily interpreted as well as more aesthetic. Point features and map labels require a slightly different set of generalization operators. Figure 3.2 illustrates that with point features as linear features, selection and displacement avoid graphic interference when too many close symbols might overlap or coalesce. When displacement moves a label ambiguously far from the feature it names, graphic association with a leader line or a numeric code might be needed to link the label with its symbol. Abbreviation is another strategy for generalizing labels on congested small-scale maps. Aggregation is useful where many equivalent features might overwhelm the map if accorded separate symbols. Here's the picture. Okay, sorry, I lost my space. In assigning a single symbol to several point features, as when one dot represents 20 reported tornadoes, aggregation usually requires the symbol to either portray the center of mass of the individual symbols it replaces or reflect the largest of several discrete clusters. Where scale reduction is severe, as from 1 to 100,000 to 1 to 200 million, area conversion is useful for shifting the map viewer's attention from the individual occurrence of equivalent features to zone of relative concentration. For example, instead of showing individual tornadoes, the map might define a belt in which tornadoes are comparatively common. In highlighting zones of concentration or higher density, area conversion replaces all point symbols with one or more area symbols. Several density levels, perhaps labeled severe, moderate, and rare, might provide a richer, less generalized geographic pattern. Picture. Area features, as feature 3.3 demonstrates, require the largest set of generalization operators because area boundaries are subject to aggregation, point conversion, and all 5 elements of the line generalization, as well as several operators unique to areas. Selection is particularly important where area features must share the map with numerous linear and point features. A standardized minimum mapping size can direct the selection of area features and promote consistency among the numerous sheets of a map series. For example, 1 to 24,000 scale topographic maps exclude woodlands smaller than 1 acre unless they are important as landmarks or shelter belts. Soil scientists have used a less precise but equally pragmatic size threshold, the head of a pencil, to eliminate tiny, insignificant areas on soil maps. Aggregation might override selection when a patch otherwise too small to include is either combined with one or more small similar areas nearby or merged into larger neighbors. On soil maps and land use maps which assign all land to some category, aggregation of too close but separated area features might require the dissolution or segmentation of the intervening area. A land use map might, for example, show transportation land only for railroad yards, highway interchanges, and service areas where the right-of-way satisfies a minimum width threshold. Simplification, displacement, smoothing, and enhancement are needed not to only refine the level of detail and to avoid graphic interference, but the area boundaries and the other line symbols, but to also reconstruct boundaries disrupted by aggregation and segmentation. Generalization often accommodates a substantial reduction in scale by converting area features to linear or point features. Line conversion is common on small-scale reference maps that represent all but the wildest rivers with a single readily recognized line symbol of uniform width. Highway maps also help the map user by focusing not on the width of the right-of-way but connectivity and orientation. In treating more compact area features as point locations, point conversion highlights large, sprawling cities such as London and Los Angeles on a small-scale atlas map and focuses the traveler's attention on highway interchanges and intermediate-scale road maps. Linear and point conversions are often necessary because an area symbol at a scale would be too tiny or too thin for a reliable and efficient visual identification. Comparing 2 or more maps showing the same area at a substantially different scales is a good way to appreciate the need for geometric generalization. Consider, for instance, the 2 maps in Figure 3.4. The rectangles represent the same area extracted from maps published at scales of 1 to 24,000 and 1 to 250,000. Enlargement of the small-scale excerpt to roughly the same size as its more detailed counterpart reveals the need for considerable generalization at 1 to 250,000. The substantially fewer features shown at 1 to 250,000 demonstrate how feature selection helped the map makers avoid clutter. Note that the smaller scale map omits most of the streets, all labels in the individual buildings in this area, and in the island in the middle of the river. The railroad and the highway that cross the river are smoother and farther apart, allowing space for the bridge symbols added at 1 to 250,000. Because the 1 to 24,000 scale map in a sense portrays the same area in a space over 100 times larger, it can show many more features in much greater detail. How precisely are symbols positioned on a map? The U.S. Office of Management and Budget addressed this concern with the National Map Accuracy Standards. honored by the United States Geological Survey and other federal mapping agencies. To receive the endorsement that this map complies with the National Map Accuracy Standards, the map is at a scale of 1 to 20,000 or smaller, and it must be checked for symbols that deviate from the correct positions by more than 1 over 50 inch. This tolerance reflects the limitation of surveying mapping equipment and human hand-eye coordination. Yet only 90% of the points tested must meet the tolerance, and the 10% that don't can deviate substantially from the corrected positions. Okay. I don't know what that was. Wait, hold on. Oh, love for the book. Anyways, I lost my spot. This tolerance reflects the limitations of surveying and mapping equipment and the human hand-eye coordination. Yet only 90% of the points tested must meet the tolerance, and 10% that don't can deviate substantially from the correct positions. Whether a failing point deviates from its true position by 2 over 50 inch or 20 over 50 inch doesn't matter. If 90% of the points checked meet the tolerance, the map sheet passes. The National Map Accuracy Standards tolerate geometric generalization. Checkers test only well-defined points that are readily identified on the ground or on aerial photographs, are easily plotted on a map, and can be conveniently checked for horizontal accuracy. These include survey markers, roads and railway intersections, corner of large buildings, and centers of small buildings. Guidelines encourage checkers to ignore features that might have been displaced to avoid overlap and provide a minimum clearance between symbols exaggerated in size to ensure visibility. In areas where features are clustered, maps tend to be less accurate in more open areas. Thus, Pennsylvania villages with comparatively narrow streets and no front yards would yield less accurate maps than, let's say, Colorado villages with wide streets, spacious front yards, and big lots. But as long as 90% of the sample of well-defined points not needing displacement meet the tolerance, the map sheet passes. Maps that meet the standards show only the planimetric distance, that is, distance measured in a plane. As Figure 3.5 shows, a planimetric map compresses the three-dimensional land surface onto a two-dimensional sheet by projecting each point perpendicularly onto a horizontal plane. For 2 points at each elevations, the map distance between their planimetrically accurate positions underestimates both overland distance across the land surface and the straight line distance in 3 dimensions. Yet, this portrayal of planimetric distance is a geometric generalization essential for large-scale flat maps. The user should be wary, though, of the caveat approximately positioned or the warning. This map may not meet the map accuracy standards. In most cases, such maps have been compiled in unrectified aerial photographs on which horizontal errors tend to be particularly great for rugged, hilly areas. Figure 3.6 shows the difference between the area's photo perspective view on the terrain and the planimetric maps of the representation of the distance at a horizontal plane because the lines of sight converge through the camera's lens. The air photo displaces most points on the land surface from their planimetric positions. Note that displacement is radically outward from the center of the photo. It is greater for points well above the horizontal plane than for lower points and tends to be greater near the edges of the near center. Cartographers call this effect radial displacement due to relief or simply relief displacement. An exception is the orthophoto, an air photo image electronically stretched to remove displacement. An orthophoto map produced from orthophotos is a planimetrically accurate photo image map. Chapter 12 examines a wider range of image maps. For some maps, though, geometric accuracy is less important than linkages, adjacency, and relative position. Among the more effective highly generalized maps are the linear cartograms portraying subway and rapid transit systems. As in Plate 1 showing the Washington, D.C. metro system, scale is relatively large for the inner city, where the routes converge and connect. Stops in the central business district might only be 4 or 5 blocks apart, and the larger scale is needed here to accommodate more route lines and station names. By contrast, towards the fringes of the city, where stations are perhaps a mile or more apart, scale can be smaller because mapped features are less dense. Contrasting colors usually differentiate the various lines. The metro system, in fact, calls its routes the blue line, the red line, and so forth, to enhance the effectiveness of the map. And by sacrificing geometric accuracy, the schematic maps are particularly efficient in addressing the subway rider's basic questions. Where am I on the system? Where's my destination? Do I need to change trains? If so, where to and what line? In which direction do I need to go? What is the name of the station and the end of the line? How many stops do I need before I get off? Function dictates form, and a map more accurate in the usual sense would not work well. Content. As geometric generalization seeks graphic clarity by avoiding overlapping symbols, content generalization promotes clarity of purpose or meaning by filtering out details irrelevant to the map's function or theme. Content generalization has only two essential elements: selection and classification. Selection, which serves geometric generalization by suppressing some information, promotes content generalization by choosing only relevant features. Classification, in contrast, makes the map helpfully informative as well as usable by recognizing similarities among the features chosen so that a single type of symbol can represent the groups of similar features. Although all map features in some sense unique, usually each feature cannot have a unique symbol, even though some maps approach uniqueness by naming individual streets or numbering lots. These maps are also very few types of line symbols to emphasize similarities among roads and property boundaries and groups. Indeed, the graphic vocabulary of most maps is limited to a small set of standardized contrasting symbols. Occasionally, the template effect of standardized symbols will misinform the map user by grouping Occasionally, the template effect of standardized symbols will misinform the map user by grouping functionally different features. Standard symbols designed for ready, unambiguous recognition in proportion for a particular scale are common in cartography and promote efficiency in both map production and map use. Traditional cartographers use plastic during templates to trace the ink and outlines of highway shields and other symbols not easily rendered freehand. Drafters would cut the area and point symbols from printed sheets and stick them onto the map and apply dashed, dotted, and parallel lines from rolls of specially printed flexible tape. Currently, graphic software allows the map maker to not only choose from the menu of standardized point, line, and area symbols provided with the software, but also design and store new fronts. Readily duplicated and added where needed, consistent symbols also benefit users of the United States Geological Survey series of thousands of large-scale topographic map sheets, all sharing a single graphic vocabulary. On highway maps, the key or legend usually presents the complete set of symbols so that, at least while examining the map, the reader encounters no surprises. A Radiohead reference. Difficulties arise, though, when a standard symbol must represent functionality to similar elements. Although a small typeset annotation next to the feature sometimes flags an important exception. For instance, a section of highway that is under construction, map makers frequently omit useful warnings. Generalized highways interchanges are a prime example of how information obscured by the template effect can mislead or inconvenience a trusting map user. The left panel of Figure 3.7 is a detailed view of the interchange near Rochester, New York between highways 104 and 590, as portrayed by the 1 over 9,600 on a scale. 9,600 on a state transportation department map. Note that a motorist traveling from the east, that is from the right, on New York 104 cannot easily turn north towards the top of the map onto New York 590. The upper right position of the left-hand map shows that the necessary connecting lanes from New York 104 were started but not completed. In contrast, the right panel shows how various commercial map publishers portray this interchange on their small-scale statewide highway maps. Two diamond-shaped interchange symbols suggest separate and equivalent connections with the eastward and westward positions of New York 104, and the large-scale map clearly indicates that a driver expecting an easy connection from New York 104 westbound onto New York 590 northbound must travel to the next exit west or south and then double back until the road builders complete their planned connecting lanes. Such discrepancies between reality and art will frustrate motorists who will assume all little diamonds represent full interchanges. Effective classification and selection often depend on a mixture of informed intuition and good working definition. This is particularly true for geologic maps and soils maps, commonly prepared by several field scientists working in widely separated places. A detailed description is necessary if two people mapping areas 100 miles apart must identify and draw boundaries for the different parts of the same feature, and these descriptions should also address the mapping category's internal homogeneity. I can't remember how to say that word, and sharpness of its contacts with the neighboring units. In soils mapping, for instance, small patches of soil B might lie within an area labeled as soil A, and this practice is because there are inclusions of soil B too small to be shown separately, and because the soil scientist cannot be aware of all such inclusions. Soils mapping, after all, is slow, tedious work that requires taking samples before the surface with a drill or auger and occasionally digging a pit to examine the soil's vertical profile. Map accuracy thus depends on the field scientist's economics. Where did I pull that from? Field scientists' understanding of the effects of terrain and geology, if known, on soil development, expertise in selecting sample points, and intuition in plotting boundaries. That crisp, definitive lines on soil map marks inherently fuzzy boundaries is unfortunate. More appalling, though, is the uncritical use in computerized geographic information systems of soil boundaries plotted on unrectified aerial photos, which are subject to the relief displacement error shown in Figure 3.6. Like quoting a public figure out of context, extracting soil data from the photographic map invites misinterpretation. When placed in a database with more precise information, the data readily acquires a false aura of accuracy. Graphic software generally play a positive role in map analysis and map display, and the notion of garbage in, garbage out notwithstanding, particularly useful to the abilities of such software is to generalize the geometric and content of maps so that one or two geographic databases can support a broad range of display scales. Large map scales presenting a detailed portrayal of small area can exploit the richness of the data, where software generalized smaller scale displays can present a smaller selection of available features. Suitably displaced to avoid graphic interference, both the content and scale of the map can be tailored to the particular needs of the individual users. Soft generalized maps of the land use and land cover illustrate how a single database can yield radically different cartographic pictures of a landscape. The three maps in Figure 3.8 show a rectangular region of approximately 700 square miles, 1,800 square kilometers. That includes the city of Harrisburg, Pennsylvania, above and slightly to the right of the center. Software generalized these maps from a large, more detailed database that represents much smaller patches of land and describes the cover with a refined set of categories. The generalization program used in different sets of weights or priorities to produce the three patterns in Figure 3.8. The map at the upper left differs from the other two maps because this computer was told to emphasize urban and built-up land. This map makes up for some small built-up areas more visible by reducing the size of the area symbols representing other land covers. In contrast, the map at the upper right reflects a high visual preference for agricultural land and more complex set of criteria-guided generalization for display at the lower left. Forest land is dominant overall, but urban land dominates agricultural land. In addition, for the lower map, the software dissolved water areas which were discontinuous because of variations in the width of the river. I'm really tired. These differences in emphasis might meet the respective needs and biases of demographers, agronomists, and foresters. Generalized maps almost always reflect judgments about the relative importance of mappable features and details. The systematic bias demonstrated by these generalized land covers maps is not exclusive to software-generated maps. Manual cartographers have similar goals and biases, however vaguely defined and unevenly applied, though the consistent application of explicit specifications. The generalization algorithm offers possibility of a better map. Yet, whether the map's title or description reveals the biases is an important clue to the integrity of the map maker or publisher. Automated mapping allows experimentation with different sets of priorities. Hence, software generalization should make the cartographer more aware of the multitude of choices, values, and biases. But that's just because a useful and appropriate tool is available does not mean the map maker will use it. Indeed, laziness and lack of curiosity are too often the most important sources of bias. The chloropleth map introduced at the right-hand elements of figures 2.13 and 2.14 is perhaps the most prime example of this bias by default. Chloropleth maps portray geographic patterns. Geographic patterns for regions composed of aerial units, such as states, countries, and voting precincts. Usually 2 to 6 gray tone symbols on a scale of light to dark represent 2 to 6 non-overlapping categories for an intensity index such as population density or the percentage of the adult population voting in the last election.
The breaks between these categories can markedly affect the mapping or the mapped pattern. And the cautious map author tests the effects of different sets of class breaks. Mapping software can unwittingly encourage laziness by presenting a map based on default classification scheme that might, for instance, divide the range of data values into 5 equal intervals. As a marketing strategy, the software developer uses such default specifications to make the product more attractive by helping the first-time or prospective user experience success. Too commonly, though, the naive or non-critical user accepts this arbitrary display as the standard solution, not merely as a starting point, and ignores the invitation of the program's pull-down menus to explore other approaches in data classification. Different sets of categories can lead to radically different interpretations. The two maps in Figure 3.9, for example, offer very different impressions of the spatial patterns of homes still lacking telephones in the northeastern United States in the 1960s. When minimal economic security demanded a landline, both maps have 3 classes, portrayed with a graded sequence of gray-tone area symbols that is implied low, medium, and high rates of phonelessness. Both sets of categories use a round number breaks, which map makers for some mysterious reason tend to favor. The map at the left shows a single state, Virginia, in its high, most deficient class, and the single state, Connecticut, in its low, most well-connected class. The casual viewer might attribute these extremities to Virginia's higher proportion of low-income African Americans to Connecticut's affluent suburbs. In regard to the remaining states, it's homogeneously average in contrast. The map at the right portrays a more balanced distribution of states among the 3 groups and suggests a different interpretation. Both states in the high category have substantial dispersed rural populations, and all 4 in the low categories are highly urban and industrialized. Moreover, a similar middle group suggests less overall homogeneity. I can't pronounce that word. I'm so tired. Oh, I'll show you guys the picture too. Oh my god. My apologies. Okay, let's get back to it, right? Machiavellian biases can easily manipulate the message of a choropleth map. Figure 3.10, for example, presents 2 cartographic treatments with substantially different political interpretations. The map on the left uses rounded breaks at 10% and 15%, forcing most states into its high, poorly connected category and suggesting a northeast with generally poor communications. Perhaps the government is ineffective in regulating and gouging telecommunication industry or eradicating poverty. Its counterpart on the right uses rounded breaks at 20% and 30% to paint a rosier, I don't know how to say that, picture, with only 1 state in the high group and 8 in the low, well-served category. Perhaps government regulation is effective, industry benign, and poverty rare. Sorry, I got a buzz. What was the other ones? Nothing good. Back to where I was. The 4 maps in 3.9 and 3.10 hold 2 lessons for the skeptical map reader. First, a single chloropath map presents only one of many possible views of a geographic variable, and second, the white lies of map generalization might also mask the real lies of a political propagandist. Intuition and ethics in map generalization. Small-scale generalized maps often are authorized views of landscape or set of spatial data. Like the author of any scholarly work or any artistic creation based on reality, the consensuous map author not only examines a variety of sources, but also relies on the extensive experience of the information or region portrayed. Intuition and induction guide the choice of features, geographic hierarchy, and abstraction of detail. The map is as it is because the map author knows how it should look. This knowledge, of course, might be faulty, or the resulting graphic interpretation might differ significantly from that of another competent observer. As it is often the case, 2 views might both still be valid. Thank you all for tuning in to the very first episode of How to Lie with Maps, or I guess Reading with Levi. That's what it's supposed to be called. I'm sorry, I'm so tired. We will be reading more than likely tomorrow. So whoop whoop. Have a great night. And if you made it to the end, like, subscribe, comment, do whatever.